All right, so we want to make sure we got some nice looking plots out of all this data we collected. So we got to do a couple things to condition the data so that we can do like a mean line with some error bars. Right? We want to find the mean of all of our data and then plot that with error bars. So one really interesting issue here is that all of our data has different lengths, right? Each period, each stride has a different amount of, say, data points associated with them. So what we have to do to kind of standardize this thing is after we make these normalizations, which remember the normalization make sure that all the data is aligned together, right? It goes from 0 to 1 and 0 to 1. That means that we can sample these data points at regular intervals and make a standard standard vector length or array length for each of our data. And there's a few ways to do this, right? The easiest way that I know is to use what's called mresize. So we can make an array called am resize. And we're going to use this function called im resize. And what are we going to pass into it for am? Well, we can put in the norm signal. And then we need to put in this this size that we want. What is the output size of the vector that we want, or the array, right? So right now am norm is like a 44 by 1, right? That's what it typically comes out as. So we can change this to anything we want. We could even go to like say 500 data points by 1, right? So this would be 44 by 1, and then it goes to 500 by 1. So what's happening? How does MATLAB do that? Well, im resize does a linear interpolation between data points to create more data or less data, right? Depending on what you're resizing to. So in this case, I could take am norm, which is 44 data points. I can make it 2 data points with im resize, and you're going to lose data, right? If you make that data longer, all it's going to do is take data point to data point, and then it's going to stretch those data and then fill in the gaps using interpolation schemes. So we can look at that if we want real quick. We say help im resize, and it's going to show you, hey, this thing is supposed to work on images, right? It's supposed to take an image and scale it up or down however we want. But what's an interesting effect of this, right? An image is just an array of colors, which are just matrices. Right? So im resize can also just work on vector arrays. And it's this really nice, neat trick to make, to do these linear interpolations of your data in one line. All right, so I got tm resize and am resize. And I'm just going to go tm norm. We can also do this with am and tm and keep that plot where we have variations in in the length of these signals, and that I'm gonna leave it up to you to decide how you're going to interpret these signals and how you're going to plot them. This has merit, right? Because it says, hey, jogging has way more acceleration than walking. So the other issue, though, right, is that do we want to look at what the characteristic of the signal is? Like the walking has this double hump thing, or the jogging kind of has this a little tiny hump. You get that better when you do these norms. When you look at the normalization here, you can see that a little bit better in the data. But either way, all this resize business is still going to work. So if we look at this TM resize and AM resize, you can see that whole thing, it plots everything exactly the same. So this is the normalized version where if we wanted to also make the non-normalized version, we could just call that IM resize norm, and we're getting a little carried away here, but it's okay. I just want to make sure that at the end of the day, you plot what you want to plot here, All right, so TM resize, AM resize, plot that, and we get standard vector or array length either way. Okay. So after we do that, we've got to take these these arrays that we just resized, and let's save these things. We don't need these anymore, this plot business. So let's say AM resize all. And what I'm going to do, I'm going to look at what AM resize looks like. AM resize is a 500 by 1 double. So if I open that up, you can see it's a column vector. Okay. So if I want to save a bunch of column vectors in a row, watch. Let's do this in the command window real quick. A equals a column vector 1, 2, 3. B is equal to 3, 4, 5. So say I wanted to save A and B right next to each other. I would I could write A comma B, right? And I would save those two columns right next to each other. So that in this version says that I need to have all the rows taken care of, and then the jth column. All right, I want to save AM resize into that, right? So this says that let's take all of the rows in AM resize, and let's say select all of the rows. I want to come down, copy, copy that, copy. And then in the jth column of AM are all right, I'm going to go ahead and paste that information. So I'm going to say AM are all of all the rows, first one, I'll say that equals this thing. All right, so what we just did, that one gets copy and paste right into there, okay? And we can do that in the program by just writing this, right? So, but that's the same thing as MATLAB is literally going to copy all the rows here and shift it into the jth column of AMR all. Okay. So we can do that for all of our variables. Then we're going to make these matrices where this is TM. This is our normalized right? AM resize norm, TM resize norm. All right, so we're making all these matrices here. And once we do that, right, we have AM, TM norm, 500 by 43. So we have 43, open that thing up. We have 43 columns, right, of by 500 data points, okay? And that's basically all the data points, all the walking steps that I had in this AM cell deal. Okay. So now we want to get mean data from all of these things. So let's see if we can't do that. AM mean R is equal to mean of AMR all. And I want that to be in the row-wise direction, right? If we just press enter right now, right, it would be in the column direction. I don't want that. So I want the second direction. So let's go ahead and just make sure that works. AM mean R, so 500 by 1. That looks like it works. So it took the vector length along the 43 data points, and it's going to make a mean of all those data points and collect that for every case in the 500 data points. Okay. So let's do this again. We'll make more data for all of these conditions, right? AMR all, TMR all, TM. Let's call that RN, TM, and TM. So we got the mean data for all these cases. And I also want to get the standard deviation. Okay. So the standard deviation STD. So we just replace mean with standard deviation. And then in here we say the same thing. Call that STD. And then the other thing that STD needs is right between that we need to put 0. So it has to be 0 too. And that's basically talking about some kind of weight information that standard deviation needs. It's like when you do max all, you have to put those extra brackets in, right? Standard deviation needs a 0 there to make sure you can do it all at once. Okay, so let's plot this stuff. Let's see, plot AM, say AM mean R, or TM mean R, AM mean R. Let's do the whole color. Let's plot this stuff real quick. You gotta hold on. Cool. So that works out. The axes are a little weird though. We should go from 0 to 1, or Oh, look at that. Isn't this a little weird, huh? This is the jogging data got widened for some reason. So why is that? Well, in here, you know, we're setting we're setting the jth column of this these matrices to whatever AM resize is. And the thing is that the walking and jogging information may have different amounts of data, right? I have maybe 43 steps versus maybe 20 or something like that. So what ended up happening is AMR all, right, kept the most amount of data. It overwrote maybe 20 out of the 44 columns. So what we need to do is take all of this stuff, take it out of our for loop, and then declare it up here. So this we got to reset this thing every time. And this, I gotta tell you, this error pops up all the time for pretty much everybody. And it happens anytime you save data in a for loop or something like that using this type of structure. Say you're trying to save data into a certain column or array or area, and you do that over and over again for different data. You have to set all of that stuff to empty, or this what's called an empty array. Or you can set it to 0, who cares? You got to set it to an empty. And then you can repopulate that thing with new data. Okay? So in this case, now let's see what happens when we plot this thing again. Okay, much better. Looks like exactly like our signal was before, where jogging was a really condensed signal and then walking was a widened signal. So it looks good. Okay, but you know, that's it's a nice mean line, but it doesn't give us all the standard deviations and stuff we want. Like we want to see how much these signals varied. And to do that, I have this other function called shaded error bar, and you can download that on Canvas. This is not a standard MATLAB function, okay? So the rules for it are a little different. If you type in help for shaded error bar, it's going to give you some information about how do you use this thing. So it says you got some X data, you got your mean line, and then you have your standard deviation of your Y data. So you have your independent axis, the mean of your dependent axis, and the standard deviation of your dependent axis. And then you got to call this thing called line props, and then you can give it a color. All right, so we got to redo this a little bit. We got to give this thing line props, then our color cell, right? And we also have to give this our standard deviation in AM mean, or AMR, right? So AM standard deviation R, take that one, pop that in. All right, and now we got we got this whole thing set up. I think it's going to work. Let's check it out. Man, that looks great. We got shaded regions for our error. So that's like how much our signal varied. And this thing is all shaded in green and red. It's transparent. You can see through data. It looks great. One thing we want to do though is kind of condition this plot, right? We want to make this thing look a little better, right? We want to talk about what data is what, maybe reshape this, reshape our limits for our x-axis and whatever. So one thing we can do real quick is come up and we can name some of our data. So let's name this thing. This one's going to be walking, and that's my first one. My second set of data is going to be jogging hand, right? And essentially, this is these legend names, we're going to have just as a description for each one of these data. And these, the order of these things is going to matter, right? We're going to have to make sure that the legend name is correspond to the same, order as our data. So some of that might get a little bit long for y'all. So one way we can make this a little neater in the code is put 3 dots, and we can press enter, and we can align all these data names, right? 3 dots, enter, align. And that way we can kind of see how it's going to run through the data. If we had to punch more, I would just keep putting these 3 dots, put in another little description, right? And then keep going. But I'm only looking at 2 sets of data right now. So, so we got this thing called legend names. So let's make a legend on our data. And to do that, I'm just going to type in legend. So now our data has this little legend up here that's going to describe which one is which, right? So this is really going to be helpful for, when you have multiple people, multiple lab mates that you're putting onto one plot. It's going to be helpful in describing which data is which, right? So we have one more concept that I'd like to show you, and that's going to be this thing called subplot. There's a way to make multiple plots in one plot. You can write subplot, and subplot kind of sets up the field of plots as an array, like a matrix. So like a 2x2 or a 1x3 or whatever. So in this case, we'll do a 2x2. In the first box, we're going to do this whole shaded error bar thing, right? With like how we've been plotting this already, right? So in this subplot, all the stuff we do here is going to correspond only to the subplot 1 of the array 2x2. Right, so we'll see. Let's just bear with me here and kind of see how that plays out. So we can do subplot 2, 3, and 4. And then here I want to plot the different stuff. I want to plot mean RN. Okay, and then I'm going to title this. I'll title that, this is error envelope. Let's call it error envelope, and this one we'll call normalized signal error envelope. And then we don't have any more real things to plot over each other, but I just want to show you how the 2 by 2 by 3, 2 by 2 by 4 work. So we're going to call this title I am plot number 3. I'll do the same thing here. I am plot number 4. So let's see what happens here. So now we have this nice looking figure where, we had our error envelope for our raw signal where we had acceleration versus time, and then we had normalized acceleration versus normalized time. All right. So what's missing on these plots is description of axes. And we should probably change these limits too for these things. So how we change limits is xlim and then we go 0 to 1 because I know this thing's normalized, so it must be 0 to 1. And then we do a ylim. And you know what, let's do this as like a before and after kind of deal. So we got subplot 2 gives me ylim xlim of 0 to 1, and we need to do x title x label. This is going to be time. Normalized time. All right. And then we'll do that up here. We'll give it x label is time. And then we'll put a unit in seconds. And let's do this as a y label. Normalize acceleration. And the y label for this one is going to be this acceleration. And that should be meters over second squared. Okay, so let's run that thing. Cool. Got our axes, normalized time, normalized acceleration, time seconds, acceleration meters per second squared. These plots look great. So when you need to plot multiple plots all in the same, all in the same figure. This is a convenient way to do that through what's called subplot. Now, let's see what happens if I want to plot one of these plots as a I'm going to plot one of these plots as a full width plot. You can see that I typed in 3, 4, and it plotted over the plot that was in 3 and the plot that was in 4. So that might be a nice way for you to look at acceleration, raw data, that might be really long, and then you can condense that into envelopes of periodic signals, stuff like that. All right, so that's kind of the gist of plotting. There's not much more to it than that. Just make sure that where it asks you to overlay each lab member's data, you go ahead and put their data in the specific order. You got the legend names. Make sure that that's their identifier. You don't have to actually use their name. You can just use an identifier, and then in the report somewhere you could just label who's who. Okay, so just kind of follow along here, and you're going to create some really nice looking figures. The one thing you can do is save the actual figure. Right? If you save the figure here as MATLAB fig version, then later, if say you restarted MATLAB or something and you just wanted to look at that figure again, you cleared everything, right? You're starting fresh. You can come in and actually open that figure up. That's all that data that is now gone because you restarted MATLAB. And you can kind of you can play around with these things, through your property editor, right? You can make these figures look really pretty. You can resize it how you like. You can say you forgot to put an axis on these things. Then all you got to do is come over here, click on this, go to more properties on the side. Let's go get this thing a little bigger. So over here, you can write in your time, seconds, y-axis, acceleration. Right, you can change your font size. You can do that per plot. So saving these things as a MATLAB figure has some good advantages.